Okay.
Yeah, so we are recording. Surely you can start
Okay.
introducing.
So, good evening, everyone. Today, the lecture will be delivered by Debarshi Das. He is postdoc with Saugata Bose's group at University College London, and he has done his PhD from Bose Institute, Kolkata. And today, he will talk about testing quantumness of gravity. Debarshi, you can start now.
Yeah,
And one moment, Debarshi. And anyone who want to ask questions, they can unmute themselves and ask the question. There is no need to raise hand. Yeah. Okay. Please, Debarshi.
yeah. Hello, everyone. Am I audible? Hello.
Yes, I can hear you.
Okay. So today I will discuss some recent experimental proposals to test the quantumness of gravity. So I will start by presenting this Einstein's field equation. This equation was originally proposed by Einstein, but later it was modified a bit. But for today's talk, this original form of the equation is sufficient. You don't need to know a lot about this equation. I'm using this equation just to motivate the topic. So in the left-hand side, this G mu nu is the curvature tensor, and this T mu nu on the right-hand side is the stress energy tensor. So this G mu nu represents how the space-time curves, and T mu nu, this stress energy tensor, represents the distribution and strength of matter and energy. So physically, this equation tells how the distribution of matter and energy in space-time bends the space-time, and how the bend of space-time dictates how to determines how an object will move in the space-time. So this equation actually connects the distribution of distribution and strength of energy and mass with the curvature in space-time. But experimentally, for the last decades, it has been shown that a mass or matter can be prepared in a spatial superposition or in a quantum state. Historically, the first experiment of quantum interference was in 1927 with electrons. But with time, people have performed quantum interference experiments with larger and larger masses. Until now, these quantum interference experiments has been realized up to 10 to the power minus 23 kilogram. So all these experiments over the last decades tells that one can prepare a mass in a quantum state. Since a mass can be prepared in a quantum state, in the Einstein field equation, the right-hand side, T mu nu, which is which states the distribution and strength of a mass and energy, it should be taken as an operator form because the mass can be prepared in a quantum state. But if this T mu nu is taken as an operator, then this G mu nu cannot be a scalar because the right hand side and the left hand side cannot be equal. A scalar cannot be equal with an operator. So what is the solution? One solution is one can make this G mu nu as a vector as well. So this gives rise to the quantum theory of gravity. Till now, various proposals has been put forward for quantum gravity. For example, string theory, loop quantum gravity, canonical quantization, and many more. All these quantum theories of gravity tells that if we prepare a mass in a spatial superposition means the mass can be here and there at the same time. So if we prepare a mass in a spatial superposition, then the gravitational field sourced by that mass should be quantum in nature. This is this class of gravity theory. On the other hand, there is also another class of theory of gravity, which is known as classical gravity, where the right-hand side of this operator d mu nu is transformed into a scalar quantity such that this g mu nu, the gravity part, can be kept as a scalar or scalar quantity. One example is one can take the expectation value of this operator d mu nu, so such that it becomes a scalar quantity. So there is no problem in keeping this g mu nu as a scalar quantity. So this is a classical theory of gravity, because here the gravity part is not taken as an operator. There are other possible proposals also. So all this kind of theory of classical gravity tells that, yes.
I have a question.
Yes.
So what do you mean by putting a mass in superposition? Like, for example, like, so you consider mass or the position of the mass in superposition or something like that?
Yes, spatial superposition. I'm telling spatial superposition. Spatial superposition
The degree
means
of freedom is the position, not the mass.
No. The mass can be here in one place at the same time in another place. This is the superposition. For example, you consider the interference experiment with electron, single electron. Then the interference pattern is created due to because the electron can travel in a superposition through both slit in double slit experiment. That is the spatial superposition of the mass, because electron has very
the mass of the electron.
That is the mass
10
of
to the
the
power minus.
yeah. The degrees of freedom that it is a superposition in the spatial degrees of freedom.
In position.
Position degrees of freedom.
Okay.
So, Debarshi, can I ask just one more question just to clarify this issue? Yeah. But I'm saying another things we can think, let's say I have some object, it has some mass. Okay.
Yes.
And let's say a few particles all together, it has some mass. So now if some particle decay from it, its mass will reduce.
Yes.
Now whether the decay process happens or not, that is the quantum process, means alpha decay, something like that.
Yes.
So now you see this mass degrees of freedom now becomes superposition. Are you getting what I'm trying to mean? So mass is 100 gram or 100, if it once decay, it is 99 gram. So it is now 100, get 100 plus get 99 by 2, something like that. What is the meaning? I don't know, but I'm trying to think in this direction. Because the alpha decay process, this is a quantum, truly quantum process.
Right.
So that you're probably not considering this kind of superposition.
No, I'm not telling about this kind of superposition. I'm telling because if a mass is in this place, it will bend the space-time in some way. But if this mass in a different position, it will bend the space-time in a different way.
Yeah.
So the question is, your point, I'm understanding.
Yeah, but I'm trying to say, let's say I put a 100 gram mass, it has bent its surroundings in a certain way. If I put 99 gram mass, it will put its surroundings in a different way.
Right.
It's probabilistic mixture also, we understand. So 99 point something. But in superposition, that will be also have some signature at the geometry in that sense.
Yeah, obviously.
If I may, sorry. The point is that in alpha decay process, okay, I think that the mass is converted to energy, then energy is quantum, right?
So when I'm saying mass and energy, I'm treating both them as identical footings, let's say, for the time being.
Yes. In this right-hand side, T mu nu, there is mass as well as energy.
Energy, it is all together I'm treating them. Okay, we can further discuss. Probably you are not addressing this kind of things.
No, I'm not. For this motivation part, I'm not telling this type of superposition. I'm telling spatial superposition of a mass.
I
But Debarshida, when you are
Yes.
saying T mu nu is a vector quantity, so this stress energy tensor of matter, this quantity is a vector quantity. What it means? I mean, if this quantity is some operator, uh, then it is much more related. I mean, I don't know about this quantity much, but it seems like okay. I mean, are you saying that this quantity is associated to the mass is superposition where degrees of freedom is space?
Yes, yes. It is the T mu nu tells the distribution of mass. Now, if a mass is created in a quantum state, for example, in a spatial superposition, then this right-hand side should be taken as a operator, not a
Okay,
scalar.
okay. And
And if it is, yeah,
if G mu nu is the operator, then what it signifies?
then it signifies quantum theories of gravity.
No,
G mu nu, G mu
but G
nu
mu
can,
nu
that
initially,
means the space-time can be also be in superposition. If the mass is in superposition of different
okay,
positions, then the gravitational field sourced by that mass should also be in
okay,
superposition.
okay, okay, okay,
Yes.
okay, got it.
So it is kind of implicit that in this T mu nu, there is not only the information about the mass and energy, it is also about the position of the system. Like because when you write it
The
as a quantum
distribution
field,
of
so
the
there
mass
could
is
be
the
uh,
distribution of the mass of space-time. So if you create
yes,
a
but
spatial superposition, then it is one type of distribution. If you don't create
yes, so it is like
superposition,
as a quantum system, if you take it as some kind of direct sum with some other system. So it is like a flag thing. So the position will give you a flag for whether it is in this position or that position. Is it like that
yes,
or
yes, it tells the distribution of mass in the space-time. So,
but in this theory, I mean in this equation, there is no I mean it is not dependent on which position you keep it, right? I mean there is
no,
no coordinate in that sense.
no,
Like
no, no.
I mean,
I
how do
mean
you
to,
set the coordinate and then you say that this is the my position or something like that? I mean,
I mean to
how it
say,
is written? In-
for example, if you create a superposition of qubit, then that state is described by a density matrix, which is an operator, right?
Yes, yes, but
Because,
I
yeah,
mean,
tell.
yeah, but then in that abstract representation, there is no position, right?
No, no, no. But here the T mu nu encodes the information about the distribution of mass in space-time. So how a mass is located in the space-time, that information is encoded in this T mu. So if superposition is created, spatial superposition of mass, then that will give one type of distribution of mass. If you don't create a special superposition, suppose a mass is in a definite position in the space-time, then it will dictate another type of distribution of mass. So this type of information, how the mass is distributed in the space-time, is encoded in this T mu. So it is the distribution of mass, just not the information of mass, how much mass, not only that, how the mass is distributed in the space-time, that information is also encoded in T mu.
Okay, okay.
Debarshida,
Yeah,
if
yeah,
I
I'm
may add
also
some.
not very expert in this gravity field, so I understand in this way.
Yeah, so can I add something?
Yeah, yeah,
Yeah, so this G mu nu and T mu nu, what you have written, these actually means it's actually a vector field, means that is actually depends on the space-time position. That means this G
yes,
mu nu is an function of x, where x is the space-time coordinates, both G mu nu and T mu nu.
yes,
Now,
X, Y,
so
Z,
what
T.
x, y, z and t.
Yes,
So now this T mu nu operator for a given x, y, z, t
that acts actually like an operator like Hamiltonian operator. Means I'm not saying it is actually Hamiltonian operator in analogous form. Now, if you give a state which is, let's say, Kate superposition of E1 and E2. So at that point of space time, it will capture that quantumness, that superposition. And on the other space time point, it will have another value. So that Somda, the question that he was asking, that T mu nu actually contains the information about the distribution of mass and energy in this sense.
Yes, yes, yes. That I'm telling.
Okay, thanks.
Can I proceed?
Yeah, sure.
So in this class of theory, where gravity is G mu nu is taken as an operator, it gives rise to the quantum theory of gravity. And there are various examples. And this type of theories actually tells that if you put a mass in a superposition of different position, then the resulting space-time will also be in superposition. On the other hand, in this class of theory, where G mu nu is kept as scalar quantity, and by different rules, this right-hand side where T mu nu operator is there is converted into scalar. In this type of classical theory of gravity, even if you prepare a mass in a spatial superposition, then also the resulting space-time will be just statistical mixture of different configuration. So in this class of theory of classical gravity, superposition of space-time will not arise because this is classical gravity. The source mass can be in quantum state, but the resulting field will be in statistical mixture of different configurations. So, for example, if you prepare a quantum source of matter in this superposition of state, where this L is the state of the mass residing in left position, and this R state denotes the state of the mass to be in the right side of configuration. Then in quantum theory of gravity, the space-time will be a superposition of this configuration and this configuration. On the other hand, in the classical theory of gravity, even if you prepare a quantum source of mass, the gravity will be a statistical mixture of this configuration or this configuration. So far, a lot of research has been done to construct various theories of quantum gravity. Mainly this part is more famous in research community. But there are people who are still working on to construct classical theory of gravity sourced by quantum matter. Until now, we don't know which theory is correct. And testing the validity of most of this theory actually requires very high amount of energy. And in fact, it can be shown that to verify these theories, we need to construct a particle accelerator of the size of our galaxy, which is almost impossible. So till now, a lot of work has been done to construct quantum theory or classical theories of gravity sourced by quantum mass. But these theories are very difficult to verify in the laboratory, as I told. On the other hand, we address a much easier question: whether gravity is quantum at all. And this question is still empirically unsettled. We still know whether gravity falls in this class of theory or in this class of theory. That also we don't know. And addressing this question, whether gravity is quantum or classical, seems to be easier to settle through a laboratory-based experiment, as I show you now. So, to test quantumness of gravity, first we have to know what do we mean by quantum mechanics. And we know that quantum mechanics is composed of various postulates. The first postulate of There is superposition principle, there is unitary time evolution, quantum measurement postulate. And in 2017, a proposal was presented which aims to test these two aspects of quantum mechanics in the context of gravity. On the other hand, we have recently proposed another proposal which aims to test quantum measurement postulate in the context of gravity. So these are the two papers which came in 2017, which aims to test quantumness of gravity, in particular the validity of superposition principle in the context of gravity. So the idea of this experimental proposal actually came from a thought experiment by Feynman, which Feynman presented in a conference in 1957. So the idea of Feynman was like that. Suppose you have a source mass and you prepare the source mass in a superposition, in a spatial superposition state. That means that the mass can be here plus there, superposition of both positions. Now, now you take another test mass. Now, if gravity is quantum, then this spatial superposition of source mass will create superposition of space-time. That means this position of source mass will create one type of space-time curvature. This superposition of position of the source mass will create another type of curvature in the space-time. But if you create spatial superposition, then the space-time curvature, and if gravity is quantum, then the space-time curvature, different configurations of the space-time curvature will also be a superposition. That means the test mass will move in superposition along this path and this path. So if you observe the test mass to be in superposition of different paths, then it will indicate that gravity is quantum. This was Feynman's idea. But at that time, the idea of entanglement or quantum information theory was not very popular. So this idea was not followed much.
Debarshi, can you repeat that thought experiment once more?
So if you prepare this mass in spatial superposition, and if gravity is quantum, then space-time curvature will also be in superposition of different configuration.
You mean that if the source mass, I can write the quantum state for the source mass, right? Then
yes. The quantum, okay. It is in superposition of this position and this position.
Okay.
And if the source mass is here, the test mass will move in this direction. If the source mass is in this location, in the below location, then the test mass will move along this direction. But if the source mass is in superposition of both of this position, then the test mass will also move in superposition of both paths.
Okay, so you have a source mass and you see how the test mass
is
moving, like the trajectory of the test mass when the space-time is in superposition and when the space-time is not in superposition.
Yes.
Right.
So if you prepare superposition of the source mass, and then if you observe that the test mass is moving also in a superposed path, then you can conclude that gravity or space-time is quantum. But if the test mass, even after creating this spatial superposition of the source mass, if the test mass does not move in a superposition of path, then you can conclude that gravity is not quantum. Or you cannot conclude anything about quantumness of gravity.
Okay. But we can say that, okay, go on, please.
One question is that when you say this thought experiment, you pre-assume that these test mass and source mass are some large mass, right? Because gravitational force is very weak.
Yeah. I'm just. This is just a vague idea. Feynman did not estimated the amount of mass which will create some observable effect. Just observe this phenomena, you need large mass, obviously.
Yeah.
This is just a vague idea, which Feynman presented in this conference, actually. So actually, this thing, this phenomena is nothing but entanglement between between the spatial degrees of freedom of these two masses. So this idea actually motivated.
Debarshi, one moment. Just go to this picture. Yeah. So for the last part of the thought experiment, just to check whether the test mass is moving in a superposition path or in some definite path. I mean, or let's say some statistical mixture path. How to do that? Or like even in
Right,
thought experiment, what is
yeah,
the way to?
it is just it will create some interference pattern if it is in superposition of both paths, just like interference experiment with electron, double slit experiment.
Okay.
In double slit experiment, the electron actually is in superposition of two paths. That's why you get interference pattern.
Yes.
How to observe this thing, Feynman did not mention. It was just an idea. So actually, this
Right.
idea was adapted later by Sugato Bose and his collaborators, and independently by Marlett and Petrel. And they came out with a solid experimental proposal. So the key idea is that,
Debarshi,
yeah,
I'm saying that suppose you are saying that mass is in the, I mean, the matter is in the superposition of both paths, as you have said that Feynman's argument. But that can be, I mean, that can also happen from the fact, right, that the gravity is classical and matter is quantum. Then also you will see
you are not creating any, a priori, you are not creating any spatial superposition with the test mass. So you have to ensure that whatever effect you are observing on the test mass is solely due to the gravitational interaction of this source mass. So you are not a priori preparing any spatial superposition of this test mass. You are preparing spatial superposition of this source mass. If it creates spatial superposition of this test mass also,
I mean, do you mean that gravity is quantum means that source mass can be in the superposition? These two concepts are same. Are you telling this?
No. Source mass, that I explained earlier. Source mass can be in superposition. There are theories, right? Where source mass can be in superposition, but the resulting gravity can be classical. That means the space-time can be statistical mixture of different.
Yeah. So in the Feynman's argument, suppose source mass is in the superposition.
Yes.
But then also gravity can be in I mean classical, right?
That is, yeah. Then you
will see.
Then you will not observe this type of superposition of the test mass.
Okay.
Because in spite of creating this spatial superposition of the source mass, if the space-time or gravity is classical, that means if the space-time is not in superposition, then the test mass will go either through this direction or through
this direction. Okay. I understood.
So creating mass is not sufficient for creating superposition of mass is not sufficient for creating superposition of space-time.
Debarshi,
Yes.
probably a stupid question. So basically, you interpret the interference phenomenon that is, that you have due to the spatial superposition as the signature of the non-classicality of gravity, right?
This is not the complete statement. Interference pattern produced by this test mass, which is solely affected by the gravitational field of this source mass.
Yes. Oh, then okay. From there,
yeah, because here I have prepared the source mass in superposition, so it will obviously give interference pattern, but it does not mean that gravity is quantum.
Yeah,
If
exactly.
due to the effect of this spatial superposition of the source mass, one can get some interference pattern on the test mass, then you can say gravity is quantum.
So you have an
You are not creating any superposition of this test mass. This is the
yes.
it is only under the effect of gravity of the source mass that is creating this superposition. If it
So
happens, then gravity is quantum.
so do okay. So do
Debarshi,
you
sorry.
Yeah.
No, carry on.
Hello. Hello.
so
Debarshita.
Yeah.
Yeah. So as you said lastly that you can think it as a kind of entanglement between this position degree of freedom of test mass and the configuration of space-time of the source mass. So it is kind of in contrast to the common like Stern-Gerlach kind of experiment, like where the thing I am sending, I am investigating the properties of that thing, like the electron. I mean, I cannot directly observe the spin of electron.
In Stern-Gerlach experiment, there is only one source, one mass. If there is
Yeah.
one mass, you cannot test anything about gravity, because to test the gravity of that mass, you need another mass.
No, I'm just saying that, but to test what spin a electron has, I actually couple it with the position degree of freedom there also, right?
Yes.
So up spin will go up and down spin will go down. So, but this position degree of freedom is the property of measurement operator, and the thing I am investigating is the spin. But here the condition is different. Like your test mass position is kind of the source, and the source mass, the gravitational configuration, what you say. So that is kind of measurement operator kind of thing, right?
Sorry, I'm not getting this part clearly. We can discuss it later.
Yeah. Maybe I.
Yes, please proceed.
Yeah, can I proceed? Okay. So the idea of the experiment is that initially we are taking two masses in a product state, and each of these two masses are prepared in spatial superposition. For example, this first mass is prepared in the state of L1 plus R1. It is in superposition of both of these two positions. And the second mass is also prepared in a spatial superposition. That means this second mass is in superposition of L2 plus R2. And by experimental design, it is guaranteed that the interaction between these two masses is only gravity, or the dominant interaction between these two masses is gravity. Now, under this configuration, if after a certain time, entanglement is created between these two masses, then it will be a proof of non-classical nature of gravity. Why? Because we know in quantum information theory that local operations and classical communication cannot create entanglement. Since all the operations that are performed on these two masses are local in nature, and it is assumed that all the interactions are also local in nature, there is no action at a distance. That means creation of entanglement between these two masses can only happen if the communication between these two masses or the interaction between these two masses is non-classical in nature. This is the idea. If starting from a product state, after a certain time, if you observe entanglement between the two masses, then you can conclude that the interaction between these two masses must be non-classical. And by experimental design, we are ensuring that the dominant interaction between the two masses is gravity. That means if entanglement is generated, it will imply that gravity is non-classical. This is the idea. Now, how much entanglement, whether entanglement is actually generated or not, to estimate that, let us consider that the gravitational field between these two masses is non-quantum in nature, and they are interacting and these two masses are interacting only through gravitational force. Then starting from a product state, the final state after certain time can be expressed in this form. And this state is actually entangled for certain choice of the parameters. So that means if gravity is quantum in nature, it will create entanglement between these two masses. Now, here, entanglement is generated between spatial degrees of freedom. In experiment, whether entanglement is generated or not, to know that you have to witness entanglement. And witnessing entanglement in spatial degrees of freedom for a large mass is very difficult, because in order to witness entanglement, you need to perform measurement at least in two mutually unbiased basis. That means you have to measure in LR basis as well as in L plus R, L minus R basis. And to realize such measurement in experiment is really difficult, because you need beam splitter, two-port beam splitter to perform the measurement. And for large mass, beam splitter does not work, because for beam splitter, you need beam splitter. The action of beam splitter actually relies on quantum tunneling. And for quantum tunneling, the transmission amplitude becomes very small when the mass becomes very high. So how to do this experiment, or how to witness the entanglement in reality? So the idea is that, suppose, let me recapitulate the Stern-Gerlach setup. Every mass can have some spin, and if the spin is prepared in the up eigenstate of sigma z, then if you subject these particles or the mass embedded with embedded spin through some inhomogeneous magnetic field, and if the spin is up, it will deflect the particle in up direction, and in the screen all the particles you will detect in this location. On the other hand, if the spin is down, then the mass will be deflected in this lower direction, and all the masses will be on the screen. You will observe all the masses in this location. Now, if you prepare the spin in superposition of up plus down, then in the Stern-Gerlach Stern-Gerlach apparatus, the spin will move in superposition of both of these paths. But at the end in screen, you will find the masses either in this location or in this location, or with some probability you will find the particle here, with some probability you will find the particle here. Now, if we remove the screen, then, if you remove the screen, then this spatial superposition will retain. Then you invert the direction of the inhomogeneous magnetic field, which will invert the movement of these masses. So initially you prepare a spin superposition, then so each mass has some spin, and you prepare a spin superposition, and you subject those masses through some inhomogeneous magnetic field that will create this path superposition. Then after a certain time, you invert the direction of the inhomogeneous magnetic field, which will close these two paths of the masses. In this way, you can create spatial superposition of a mass. Now, in this way, if we create spatial superposition of each of these two masses, and if these two masses interact only through gravity, then at the end, if gravity is quantum, then entanglement will be generated between the spin degrees of freedom of the two masses. Because initially, entanglement is generated between path degrees of freedom. And here, path and spin are getting entangled in this Stern-Gerlach interferometer. At the end, due to entanglement swapping, the entanglement generated between the path degrees of freedom will be transferred to spin degrees of freedom. That means at the end you will get entanglement between the spins of the two masses. And whether spin entanglement is generated or not, that can easily be verified by measuring spin correlations. So this is the idea to do the experiment. Now, you have to ensure that the dominant interaction between these two masses is gravity. One can do it in principle. One can neutralize the masses, and that can cancel almost all electromagnetic force interactions between the masses. And also there are techniques to get rid of charge multiple interactions or magnetic dipole interactions between the two masses. Those are not very easy, those techniques, but physicists are adapting those techniques very routinely in different contexts. But there is one type of electromagnetic interaction that you cannot cancel by neutralizing masses or by adapting this type of techniques. This interaction is Casimir interaction. So this Casimir interaction is actually becomes effective when the distance between the two masses is very small, because this interaction is short range interaction. So one way you can make the distance between the two masses very large, but since gravity is a very weak interaction, if you place the mass in a long distance apart, then the gravitational interaction will be very weak. So you have to keep the two masses close enough to each other. But if the distance between the two masses is very small, then this Casimir interaction will be dominant. So there should be some minimum distance above which the gravity will be dominant compared to this Casimir interaction. So people have calculated what is the minimum distance between the two masses such that the gravitational potential will be at least one order of magnitude larger than the Casimir interaction. And if we consider the system to be a diamond with nitrogen vacancy center, where electronic spin can be embedded in a mass, then such minimum distance is found to be 157 micron. That means the minimum separation between the two masses must be larger than 157 micron in order to guarantee that gravity is dominant compared to other forces. So one possible practical parameter regime is that if you take masses of the order of 10 to the power minus 14 kilogram, and if you keep the minimum distance between the two masses of the order of 200 micron, which will guarantee that gravity is dominant compared to the Casimir interaction, the interaction time between the two masses is taken to be 1 second, and the superposition size, that means the distance between the left and right arm of each mass, if it is taken to be 100 micron, it will guarantee enough detectable entanglement. And the interesting point is that this type of mass scale has already been prepared in pure state by different groups all over the world. So the problem in dealing with large masses is that it is very difficult to prepare a pure state, because in any material, atoms move randomly or wiggle randomly. So if you consider the mass as a harmonic oscillator system or some other system, since the atom moves randomly, that means the energy of those masses are not in the lowest energy eigenstate or ground state. And in different runs, you cannot control the movement of the atoms or the motion of the atom. So in different run, the system will be in different energy eigenstate. So as a whole, the mass will be in a mixed state. So the initial criteria to do any experiment with large mass that you have to prepare pure state. Otherwise, you cannot do any quantum experiment because mixedness destroys coherence and all. So people, researchers all over the world has actually realized pure state of this order, 10 to the power minus 14 kilogram or 10 to the power minus 15 kilogram. People have prepared pure state by ground state cooling. So this makes this experiment realizable with near-term technology because the initial initial requirement for this type of experiment that you have to prepare the mass in a pure state. Even before preparing the superposition, you have to prepare the mass in a pure state. That has already been achieved in by various groups. And this is actually the main discovery of these two papers, that with such type of mass, you can do an experiment which can tell something about quantum gravity. This is the main achievement of these two papers. Now, in 2017 proposal by Sugato Bose or Marletto Vedral, it was shown that if decoherence rate is above a certain threshold, then no entanglement will be generated. And if entanglement is not generated, that means the protocol will fail. So, however, for even such high decoherence rate, the coherence in spatial superposition, you are initially preparing a spatial superposition of the masses. So even for such high decoherence rate, when there no entanglement will be generated, even for such high decoherence rate, the superposition is not completely lost. So the question remains, can this remaining superposition be exploited to observe some other non-classical effect of gravity? The next drawback of 2017 proposal is that it requires realizing entanglement witness operators. That means it requires this completely trusted measurement devices of sigma x, sigma y, sigma z, etc. But in experiment, it is again very difficult to trust your measurement device in each experimental run. But one can bypass this requirement by detecting entanglement through a Bell test. But the problem is with Bell test is that there are various loopholes, and closing various loopholes in Bell test is actually very difficult. And also, detecting entanglement through Bell test requires even lower decoherence rate because not all mixed entangled state are Bell non-local. So the question remains, can we propose a new experiment to test non-classicality of gravity that does not require trusted measurement devices? And finally, in these two papers by Carlo Rovelli, Kassler Bruckner, they have shown that if entanglement is witnessed in those experiments, then it will imply that the space-time or gravity obeys superposition principle. They have used quantum field theory approach to show that if entanglement is witnessed, that will mean that the space-time is in superposition of different state. But even if entanglement is witnessed, then the question also remains, does gravity obey quantum mechanics? Or does gravity obey some other non-classical theory that supports superposition principle? Because there may be some non-classical theory that we may not know till date, where superposition is a part, but which is different from quantum mechanics. So if this experiment becomes successful, then this question remains that whether gravity is quantum or whether gravity is some other non-classical, obeys some other non-classical theory that supports superposition principle. So in order to deal with such questions, more and more quantum mechanical postulates should be tested for gravity. So in order to answer this question, we have recently proposed another new experiment. And this experiment, we have shown that works for any finite decoherence rate It does not require any trusted measurement device, and it tests a specific aspect of quantum measurement postulate, which is different from quantum superposition principle. So what do we mean by quantum measurement postulate? There are various parts of quantum measurement postulate. There is quantum measurement induced disturbance or collapse, and we are actually aiming to test this particular aspect of quantum measurement postulate. Another one is that always one measurement outcome is observed in a single run. It is always observed. There is nothing to test here. And the outcome probabilities are given by Born rule. And we are not aiming to test Born rule for gravity. So the idea of this experiment can be vaguely represented using the double slit experiment with electron. If you send an electron through a double slit, you will obviously observe interference pattern. People have observed it in various experiments. Now, if you place a detector to perform which path measurement, that means to know along which slit the electron is passing, then interference pattern will disappear. And why it is happening? Due to quantum measurement induced collapse of disturbance. Now, if we can do the same experiment, so our proposal is that in the first part of the experiment, we will suppose we observe interference pattern with electron. Then in the second part of the experiment, instead of doing which path measurement, we are performing measurement of the gravitational field of the electron. And if due to this measurement, if the interference pattern disappears, then it will imply that gravity is non-classical. Why? Because it will imply due to this measurement of gravitational field, the superposition of the space-time is destroyed, which is destroying the spatial superposition of this electron. Because the space-time curvature determines the distribution of mass, whereas also mass distribution determines the space-time curvature. So if you disturb the space-time curvature, that will disturb the distribution of the mass in the space-time. So if you observe this type of disappearance of interference pattern due to measurement of gravitational field of the electron, it will imply that by doing measurement, you are collapsing the space-time or the gravitational field in a particular configuration. That means gravity is not classical. Obviously, the experiment cannot be done in this way. So, how much time I have? Hello?
Maybe
You take 5-6 minutes more, I guess.
Okay.
And after that, question, I guess.
Okay, so I will not go through the whole details of this experiment. So, yeah, in order to properly formulate this experiment, we need few concepts about classical field. So, classical field can be defined by various conditions. For example, it is number valued at each point in the space-time. It is not operator valued. Classical field means at each point there is a number, not an operator. And one can in principle observe those number of space-time without disturbing it. And these two conditions gives rise to the non-disturbance condition, which means that the act of performing an intermediate measurement should not influence the outcome statistics of a subsequent measure. Because in classical field, you can observe or you can measure the value of the field at any point without disturbing the system. That means any intermediate measurement should not change the outcome statistics of a subsequent measurement. So,
Debarshi, hello.
yeah.
Debarshi,
Yeah, tell.
Actually, some of us are saying that, okay, if you go through the details in this experiment, it would be very interesting. So if you
So,
want, you can take another lecture also.
Yeah, that I can do.
Yes, yes.
I mean,
Next
next week anyway, you have the plan to discuss
yeah,
something, but you can
yeah,
start from here and you can continue this and then
right.
continue much
True.
better. So maybe you can conclude
So
for
I'm
to-
concluding on only the first experiment. So let me conclude. So if entanglement is detected in the 2017 proposal, the odd part I'm not telling because I will tell it in my next talk, then it will rule out all such classical theories of gravity. It does not tell which quantum theory of gravity is correct, but it will at least rule out all such possible classical theories of gravity. So this is the main essence of the 2017 proposal or our new proposal that I will present later. So whether gravity is quantum or classical, that is still an open question. We don't know.
But Debarshida,
Yes.
I have one question. For example, suppose I go back to the Bell scenario. If suppose I'm doing 2 input 2 output CHSH Bell test, okay?
Yes.
And suppose I see there is a no non-locality.
No non-locality. You are not. That means you are not getting
Suppose I have
violation
an
of.
entanglement state. Let's I have a Warner states.
Yes.
Okay. And then I am doing 2 input 2 output Bell test.
Yes.
And then I'm not finding any non-locality.
Yes.
So then I cannot immediately say that, okay, that state is not quantum. For example, if even the state is entangled, I can give some local model of it. So when you are initially saying this classical gravity things, I was thinking that, okay, you have some things which may be quantum. You try to explain it classically. Sometimes it might happen that just like a local hidden variable model, I can be very fortunate and can give, for some phenomena, I can give some classical gravity model for some phenomena. So what I'm saying, whatever you are observing, it might happen that very particular type of quantum phenomena you are observing. For that things, it might happen that, okay, I understand. And negation part, that, okay, if you find positive result, then obviously this classical gravity model will fail.
Right.
But if you don't see positive result, then still
Then
this
we can't tell. Then we can't tell anything.
Exactly. Okay. I mean, so this classical gravity model is like the same things like a local hidden variable type of model, right?
It is not.
For some phenomena.
It is like local hidden variable test in Bell non-locality. So violation is only important. If you don't get any violation, you can't settle anything.
Okay. Mahinda, you don't need to raise hand. You can directly ask questions, I think.
Yeah, what I'm trying to say, you don't have to think, bring this LHV here. You try to think if it is a positive result, then certain conclusion. And if it is not positive result, okay, we are silent.
Yes, exactly.
Now, whether device independent, not device independent, that is a different story. For the time being, here our fundamental assumption is that as we start from quantum information theory, that by LOCC we cannot create entanglement. So some entanglement is generating, so some signature should come.
Yes.
Yeah. So Debarshi, can I ask one question?
Yeah.
So since you will give a talk in next week also, that will be great. So but there is a recent work by this Miguel Navascas and Trillo.
Yeah. Right.
We are putting some concern that not all possible classical theory you can exclude, particularly this Penrose-Dosoi model.
Diossi model. They are claiming that with Diossi model.
And what they are saying, that has some reason actually. So it would be good if you can next day some part you can cover. Okay, you can have a look at least.
Yeah, actually, I have tried to look at it, and these papers are written from quantum field theory those
No,
type
no,
of
no, there
like,
is no field. No, 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 there is no field theory, nothing. It is just standard things. Just
Really?
one point you have to understand. I'm saying at the page 2 at the end, there is, however, a flaw in the reasoning above. The dynamics of
Okay.
model of classical gravity do not necessarily decompose into sequence of pairwise interaction between each massive particle and classical field. This is a certain kind of classical theory which Penrose-Dawson model necessarily need not to or any classical gravity theory need not to necessarily satisfy that condition. Which is example Penrose-Dawson is a one example.
Right.
It is
Yeah, I have
no field theoretic
Okay.
approach is there. I think if you
Okay,
just
okay.
have a look, you can give
Yeah,
a better idea.
Yeah. I will try to before my next stop.
Yeah, if nobody has other question, I can ask one more question. So you can go to this Feynman test proposal once again. Can you just? Yeah, just one slide. Okay. So let's say I'm saying that is a good. Means Shogotodas and Bhadral motivation comes from here. No, you are telling.
Yeah.
In a sense. So now, if source mass is superposed, so I'm saying now your test particle, you are taking a massive particle.
Yeah, in Feynman thought experiment, there was no limit on mass.
No, I'm not talking about the amount of mass, all these things.
Okay,
but I'm saying let's say this test particle is a photon.
Yes.
Okay, so if the source mass is at the downside, what will happen? So photon will bend towards that bending of light phenomena.
Yeah, due to electromagnetic interaction.
Due to
electromagnetic interaction and due to
no bending of light. Why electromagnetic interaction?
Oh no. You are telling photon, right?
Yeah, I have a massive particle. So if I send this light, it will bend. This is a gravitational phenomenon, no?
Right.
That is the first test of GR.
Right.
Okay.
Right.
So this mass, this photon or light will bend towards the lower mass. If I put the mass upper direction, it will bend towards up direction.
Right.
Now I am saying let's treat my photon to be as classical quantum particle.
Yeah.
So we have this, we can prepare photon in classical state. By classical, my definition of classical is, it is Sudarshan-Glover, P distribution is positive.
Okay.
So if one mass I put at downside, so it will be, so if there is no mass, I will get a Sudarshan, I will get a distribution of Sudarshan-Glover. Of course, distribution we cannot make. That's some what is called Mendel P factor, all these things we can experimentally measure. That I will measure. And this positivity, if it is positive, it has some signature that I can measure. And due to bending, it will some shift will happen.
Yeah. Right.
If it is upper direction, shift will happen in upper direction. So if the mass is probabilistic mixture, there is a theorem that probabilistic mixture of coherent state will coherent.
Okay.
Coherence means this P distribution positivity with probabilistic mixture that will remain positive.
Okay.
But if something negative I get, that proves something very peculiar is happening, because it is not anymore probabilistic mixture.
Right.
Have you seen anything this kind of work in literature or something? Because since you are exploring that direction or all these things.
Yeah, no, with photon, I have not seen any type of this type of.
There might be lots of other things, other.
Maybe gravity from gravity background people may have explored, but I have not seen.
I see.
From gravity background. But in this direction, quantum information background, I have not seen anything about it.
So you are telling something.
Yes. I was saying that, like, okay, so bending of light is a gravitational phenomenon, but it also requires like a very large mass, no?
No,
because
that I am saying for the time being, it is a thought experiment. Now, very large mass, that experimentally, in some sense, you can manage it. You do so do the what is called neutron interferometer, but instead of one neutron beam, we will send multiple neutron beam. So in a sense, mass is increasing in a sense, no? That somehow experimentally, up to certain level, it can be manipulated. Means experimentally, it can be taken.
Of course, I
But
mean, one can actually compute the
and
scale
also-
size things.
yeah,
can be-
all these are technical question, because whether if the effect comes out at the order of 10 to the power minus 24, then of course it is at the thought level only. We cannot do experiment with the present technology.
And also, I have one point regarding this type of thing. Whatever you are telling, you are assuming that there is only gravitational background.
Exactly.
I mean, space-time background. But in experiment, there will be other interactions. So
Yeah, that's the thing. That's
Yeah.
the thing. Yeah. The actual
Maybe-
point will come if we can means neglect all the other. There is a way out that we can neglect all other possible things. But here,
Yeah.
one thing is good, that photon is comparatively less interactive particle. No photon. That is a good thing.
yeah, but electromagnetic interaction.
So that shielding effect we can in principle experimentally put. Electromagnetic
Yeah.
shielding effect is in principle possible in a small region that can be implemented.
Right.
Of course, this is one possibility. Now you are saying in your experiment also some other effect you are mentioning. What is it called? You just mentioned no other effect, something cashier effect or some all these things.
Casimir is also electromagnetic interaction, and it can be also shielded by
I see,
Faraday's
I see.
screen.
I see. So
So
whether
actually, yeah, the parameter regime that I mentioned, this can be made less demanding by putting a screen between two mass, Faraday's screen.
I see. But in next talk, if you can make some comment regarding this, what you call,
I will try to have a look
that
at
will be
it.
great.
Yeah.
Thank you.
Okay, so let's hold your questions for the next week. And thanks, Debarshi, for the nice talk. And we'll see you next week. Okay, bye, everyone.
Okay, bye.